Hey Team Pika, and welcome to today's lecture, where today we're going to be talking about electronic spectroscopy. So to recap from last time, we've talked about vibrational spectroscopy, now we've talked about rotational spectroscopy, and the processes involved between the two types we learned were pretty similar. With rotational spectroscopy, we once again followed our flow chart, modeling the potential, solving for the wave functions and energies, discussing the allowed transitions, and then trying to understand how that relates to an experimental spectrum. With rotational spectroscopy, the type of motion we were studying was free rotation of a molecule about a fixed bond length. The wave functions associated with that motion end up being spherical harmonics, and the energy expression is pretty simple, where the energy levels are given by the expression B, where B is a product of a bunch of different constants. Planck's constant h bar squared divided by 2 times mu, the reduced mass, times r, the bond length squared, times j times the quantity j plus 1, where j is our rotational quantum number. And based on this expression, we saw that the various rotational energy levels are increasingly widely spaced apart as we go up in j values. Not shown on this review slide, but something that is true in general is that as we go up in j values, we also get a larger number of states since the degeneracy goes up by quite a bit. Our selection rules for rotational spectroscopy were, first of all, that our molecule had to have a permanent dipole moment, and secondly, that if we're going to change rotational levels, we either have to go up a level or down one level. The expression for our transition energies, we got through some simple algebra of taking the energy of the j plus 1th level and subtracting it from the jth level, and that gives us a transition energy of 2b times j plus 1. How that relates to our microwave spectrum is that various peaks in the microwave spectrum can be assigned to different translational or different rotational transitions. At room temperature, rotationally excited states are naturally present, and so unlike vibrational spectroscopy, we got more than one peak. We can also use our delta E expression to assign what energies correspond to these transitions, and we see that the energies go up in increments of 2b. And so that is why our rotational spectrum have these nicely spaced apart peaks that corresponds to various available transitions in the spectrum. Something that we didn't talk about last time, but that we'll learn a couple lectures from now, is why the intensities of the peaks, so the amount that those peaks show up on the y-axis, why those differ between our rotational levels. But for now, let's talk about electronic spectroscopy. I have 3 goals for today's lecture. The first goal is for us to talk about electronic spectroscopy for hydrogen-like atoms. We'll talk a little bit about the selection rules and how it is that we know that these transitions show up in the UV vis area of the electromagnetic spectrum. The next thing that we'll do is we'll briefly talk about electronic spectroscopy for multi-electron atoms. This is a complicated topic that could be the subject of multiple lectures, so I'm going to give us just a very brief overview along with a little bit of the notation that you might expect to see if you're listening to a lecture or a seminar later on where someone is discussing multi-electron spectroscopy. So we'll talk about how the electron configurations that we learned about in general chemistry relate to spectroscopy notation called term symbols, and how that helps us depict electronic wave functions for entire atoms. And once again, we'll discuss briefly what selection rules are associated with these transitions. And then last but not least, and what I think will probably be for most of us the most fun part of the lecture, is we're going to talk about the various principles that are associated with electronic spectroscopy for molecules. We'll talk a little bit about selection rules, but most of our focus will be on understanding 2 processes that you may have heard about in real life, fluorescence and phosphorescence. So if you've ever wanted to know how our light bulbs work, the fluorescence part of today's lecture is for you. And if you are fascinated like I am by glow sticks, why they glow for so long, and how that works, we're going to talk today about what is the underlying principle behind phosphorescence. In trying to understand what transitions are possible, last but not least, we're going to bring up a little bit of information about how vibrational motion can be associated with electronic transitions, and that'll lead us to something called the Frank-Condon principle. So with that, let's go ahead and get started. At the beginning or near the beginning of this lecture series, we discussed in great detail the potential energy, wave functions, and energy levels that are associated with a single electron atom, so-called hydrogen-like atom. We have our nucleus with a positive charge that is the magnitude of the electron's charge times z, the atomic number. And then we have our electron itself, which has a negative charge with a magnitude related to this E constant, that's just the charge of an electron. In that case, Coulomb's law tells us that the potential energy of an interaction between an electron and that nucleus is equal to negative, because it's an attractive interaction, times z, that atomic number, times E squared, divided by a couple of constants, 4 pi epsilon naught, and also divided by r, the distance that separates the electron from the nucleus. After a lot of intense work, we finally figured out that the wave functions associated with this hydrogen are a product of the radial wave function, which has long-range exponentially decaying behavior, and in the intermediate range has some polynomial terms that are best looked up in a table. And then multiplied by that is our angular wave function, or our spherical harmonics. And so based on this wave function and the associated quantum numbers, n, l, and m sub l, we can see what the shape or the electron density distribution is for any orbital that we're interested in putting an electron in. Related to these wave functions are the associated energy levels, which we have to remember for hydrogen only depends on n, not on both n and l. Our expression for the energy levels in the hydrogen atom are a number of constants multiplied together times a negative number, because again, it's an attractive interaction, so we get a net stabilization of the energy in the electron and the nucleus interacting with one another. And then it's times z squared, the atomic number. So the energy levels go down as we go along the periodic table, and divided by m squared. So lower quantum numbers are associated with more stable energies. So our energy level diagram for the hydrogen atom ended up looking something like this. Again, because it's not a multi-electron atom yet, doesn't matter what my value for L is, just N is going to determine the energy level. And so in order to understand if I have an electron, say starting off in the ground state, if I want to understand what transitions this electron can undergo, we have to think about the selection rules for the hydrogen atom. That means we need to solve for the transition dipole moment and plug in the wave functions associated with the hydrogen atom. By convention, you'll see me pretty frequently during today's lecture using primes to distinguish between excited and ground state. There's not necessarily unanimous consent over what primes mean what. Does it mean the ground state or the excited state? But it really helps distinguish between states. So you'll see me use that notation in today's lecture. Once we carry out the integral, we find that we have a couple of selection rules. Somewhat surprisingly, there's no restriction on changes in n. So we can jump up from the n equals 1 level all the way to the n equals 5 level, if we so choose. In terms of L, the change in our L value does have to either go up by 1 or go down by 1. And kind of like we saw in rotational spectroscopy, changes in our m sub L quantum number, m sub L either needs to not change or to go up by 1 or down by 1. And last but not least, during our transition, m sub s, the spin quantum number, is not allowed to change. So if the electron starts spin up, it's going to end spin up. And if it starts spin down, it's going to end spin down. Let's practice a little bit with these quantum numbers. Go ahead at this point and pause the video and try and see if you can determine which of the following transitions for the hydrogen atom would be allowed according to the selection rules that I've just given you. For C and D, I've given the notation using our, tuplets of quantum numbers rather than using our chemist notation. So for C, you should read the quantum numbers in order: N, L, M sub L, M sub S. So pause the video and see if you can determine which of these transitions are allowed. All right, welcome back. So for our first transition, this transition ends up being forbidden. Going from an s orbital to another s orbital would mean that delta L equals 0, and that's not in line with our selection rules. However, the second transition, B, is allowed because we're changing the electron from being in an s orbital in its initial state to being in a p orbital in its final state. As for item C, we see that looks like N is fine. Again, we don't have to worry about N for our selection rules. Our change in L is good. It's going up by 1. But our change in M sub L in this case is not good. We are changing M sub L by too much. And so this would be a forbidden transition. Another way that you could see that it's forbidden is that I'm going from a spin up state to a spin down state. And so that is 2 reasons why this transition would be forbidden. And as for D, all of our changes in quantum numbers look good, but it tricked us. This doesn't correspond to an orbital at all because it doesn't obey the rule that N has to be greater than L. So this one was a bit of a trick question because this one's not an orbital. In diagram form, the allowed transitions for our hydrogen atom can be shown in what's called a Graphian diagram. Here, the degeneracies of our various M sub L levels aren't shown, but you can see the transitions between different values of L. Like you learned about in your general chemistry class, one way to observe these transitions experimentally is via a gas discharge lamp, in which you insert a sample of your hydrogen, you pass an electric current through that sample, and that's enough to generate electrons in your hydrogen atoms in an excited state. As those electrons eventually undergo a transition, either back to the total ground state or just to a lower excited state, a photon gets emitted. And lots of different regions of the electromagnetic spectrum can result from these types of transitions, but by far the most famous ones are the ones where the final state of the electron is in the N=2 level. So a question that I'll pose for us, and that you actually answered in your general chemistry class, and that we're going to do as part of our in-class activity, is, in that case, what electronic transition is responsible for the emitted photon that has a wavelength of 410 nanometers? Again, this is something that you've done in GChem, but hopefully you can use the review that we've done in physical chemistry, especially for how to go from our energy level diagram to an associated photon wavelength to figure out what the initial state of the electron must have been in this case. But for now, let's talk about electronic transitions from multi-electron atoms. In general chemistry, and up until this point in the course, you should hopefully be familiar with using electron configuration notation or electron configuration energy level diagrams to depict the electronic state of a multi-electron atom. So for example, with carbon has an electron configuration of 1s2, 2s2, 2p2, and if I use the alpha principle and Hind's rule in order to populate our energy level diagram for all of these single electron orbitals with electrons, then you end up with the diagram shown at right. However, both of these types of notations or ways of depicting where the electrons exist in carbon are a little bit deficient or ambiguous. You may not have thought too much about it, but the electron configuration notation shown at left doesn't give us full information about which 2p orbitals are being occupied when carbon is in this configuration. And especially if we're trying to talk about possible transitions that this carbon atom could undergo, maybe a transition where the electron in my 2p orbital undergoes a spin flip, or where we disobey Hind's rule and excite the electron by putting it into the same orbital, as my first electron in the 2p orbital. Just writing the electron configuration would be too ambiguous for us to be able to communicate that information. And as for the energy level diagram at right, there's too many lines on this diagram. Each of these lines on the diagram you're used to represents a single electron wave function. But when we're talking about electronic transitions, we need to be thinking in terms of the overall multi-electron wave function, which, if you remember back from lecture 8, according to the orbital approximation, is roughly the product of all the single electron wave functions. So for today's lecture, on thinking like electronic spectroscopists, we need to transition our thinking from the diagram at left, this blue diagram, depicting all of our single electron wave functions, to more of a multi-electron wave function, where you'll notice that capital psi, or the multi-electron wave function, is a product of the individual wave functions, and energy is approximately a sum of the individual one-electron energies. Psi is a way of depicting in the abstract what's happening with this carbon, but we would like there to be some sort of unique and consistent notation for describing what these multi-electron overall wave functions look like. And so electronic spectroscopists use something called term symbols to depict what electronic state a particular atom is in at a particular moment. Term symbols have two pieces to the notation. There's a superscript that shows up in the upper left-hand corner that describes the multiplicity of the system. We've talked a little bit in this class about multiplicity, especially in lab. And so remember, the multiplicity, capital S, is the sum of all of the m sub s values for our electrons, which means that the easiest way to think about multiplicity is by looking for the number of unpaired electrons, adding one to that, and calling that your multiplicity. So for example, with carbon, there's 2 unpaired electrons in the configuration that I've depicted on this slide. And so our multiplicity is 2 times the m sub s value. So we get 2 unpaired electrons plus 1. That's a triplet state. The second piece of our term symbol notation is we're going to use an English and or Greek letter to represent the total orbital angular momentum of the system. What letter we choose to use depends on what type of system we're considering. So there's different notations and different letters for our hydrogen-like atoms, which should be familiar to lowercase s, lowercase p, lowercase d, lowercase f, to depict our L values, that orbital angular momentum term. Also, you've seen before this sigma pi notation when we're talking about molecular orbitals. What's going to be new to us is that for multi-electron atoms, we're going to use capital S, P, D, and F to talk about the total orbital angular momentum of a multi-electron atom. So how do we do that in practice? This is one of those topics where there is a lot of information about how to generate term symbols, not just for carbon, for instance, in its ground state, but all the different possible excited states it could be in. And to really understand what are the degeneracies associated with those term symbols? How many different states correspond to a particular electron configuration? We're not going to do any of that, although I'll post a link on Moodle to a really nice lecture video that describes that topic. What we're going to focus on today is how to generate the term symbol for the ground state of a multi-electron atom. And you can do it by following these 3 steps. First off, draw your energy level diagram, just like you're used to in GChem. Place your electrons so that it obeys Hooke's rule and the Aufbau principle. And then a new caveat, fill the electrons into orbitals in such a way that you fill the higher levels of m sub l first. And so with those, I like to do this by simply labeling my orbitals. S doesn't matter, L is always 0. But for P and D orbitals, I'll label the biggest values of m sub L on the left, the most negative values on the right, and then I'll fill in my electrons the way that I was taught in my general chemistry class. So you can see for carbon here, I filled in my first electron into the m sub L orbital with m sub L equals 1, because that's the highest value. My next electron, I don't want to disobey Hooke's rule, so I'm not going to place it in that orbital as well, but I am going to place it in the m sub L equals 0 orbital, since that's the next highest value that's available to me. Once I've drawn that energy level diagram, then it's up to me to determine the multiplicity and the total orbital angular momentum. Like I just said above, here carbon appears to have 2 unpaired electrons. So this is going to be a triplet state. And I'm going to write for my term symbol a 3 in the upper left-hand corner of the term symbol. Secondly, I need to determine the total orbital angular momentum, which means that for each electron, I'm going to sum up the m sub L values. For my s orbitals, m sub L is equal to 0, so I don't really need to worry about that. And looking at my electrons that are in the 2p orbitals, I have one electron that is in m sub L equals 1, and one that's in m sub L equals 0. So 1 plus 0 is equal to 1. And then we're going to use that information along with the table that I just showed you above to determine the appropriate letter to use for the term symbol. So since our orbital angular momentum quantum number is equal to 1, I'm going to use a capital letter P in order to depict the term symbol. So overall, that means that carbon's ground state term symbol is 3p, which you should read off as being a triplet p state. Let's do another example. See if you can use these steps, and I'll zoom out a little bit so that you can also see the table. See if you can use these steps to determine the ground state term symbol for nitrogen. Pause the video, and we'll come back and go over it once you've done that. Okay, so our ground state term symbol for nitrogen is pretty similar to that of carbon. We just need to add in one more electron for nitrogen so that it has a total of 5 valence electrons. In that case, now I see that I have 3 unpaired electrons, so my multiplicity is going to be 4. My m sub L values, when I sum them up, now I have 1 plus 0 plus negative 1. That gives me a total value of 0, which corresponds to the letter capital S. And so this will be nitrogen in its 4s state. Or, if you like, quartet S state. So I bring up all these issues of term symbols because you may very well see, either in a seminar or in a lecture series, an energy level diagram for a multi-electron atom. And I don't want you to be surprised when you see each horizontal line not depicting where a single electron goes, but depicting what the overall total energy is for an atom in a certain electronic state. And so, based on these diagrams, we don't want to populate this with electrons because, again, it's not representing the same single electron diagram we're used to from GChem, but instead it does allow us to see what transitions this atom can undergo electronically as a whole. It's very similar to our selection rules for hydrogen. The selection rules for multi-electron atoms are that we can't change spin states, and we have to change the total angular momentum by plus or minus 1. And so on this Brownian diagram for carbon, I've shown you both an allowed transition in green, going from a triplet P state to a triplet D state. We're not changing the multiplicity, but we are changing the orbital angular momentum. And I've also shown you a forbidden transition, going from a triplet P state to a singlet S state. Not allowed because we're changing our spin state in that case. All right, and last but not least, let's talk about electronic spectroscopy for molecules. To understand these electronic transitions, we first have to understand a little bit about the potential energy surfaces associated with both the ground and excited electronic states. By potential energy surface, I mean that we're trying to graph the energy of the system on the y-axis versus either a bond length for a diatomic molecule or for a polyatomic molecule, a more complicated all the sets of nuclear coordinates and what might change. So for simplicity, I'm going to make our x-axis kind of abstract. We'll just call it a generic or representative nuclear coordinate. But in your head, you can think about how this would work for a diatomic molecule, where our x-axis would be the bond length. So the diagram above is combining information about the electronic states available to the system with the vibrational states associated with each electronic state. And so all of our horizontal lines in the diagram refer to what vibrational states are possible. And you'll notice that, again, I'm using my prime notation to try and depict the difference between the ground electronic states, vibrational states, and what's happening in the excited electronic state. So because the excited state is typically a weaker bond than the ground state, we'll see that the vibrationally excited states in our electronic excited state have smaller bond force constants. We get to a little bit bigger equilibrium bond distance in the electronic excited state, and typically our dissociation energies, for how much energy it takes to break the bond, is smaller in the excited state compared to the ground state. We don't have time to talk too much about the implications of this fact, but you could imagine that this would be really important in thinking about photoexcited reactions. And in fact, that's a really active area of exploration in organic chemistry, is how you can use light to weaken or activate bonds instead of the typical molecular catalyst that you may have learned about. So if we have a couple of different excited states, there are many different types of electronic transitions that can happen. And we're going to take a little bit of time to consider each of these possible transitions in turn. The first type of process that we might see for a molecule is absorption. Absorption is the process by which a molecule is excited from the electronic ground state up into the electronically excited state. And on my diagram, I've depicted this absorption process using a red arrow. The bottom depicts where the electron or where the molecule is starting. The top of the arrow depicts its final resting state. There's a couple of key features to point out about how absorption works in practice. Selection rules for molecules are a little bit relaxed compared to those for atoms. We don't need to worry about the orbital angular momentum of a molecule, but we still do need to worry about its spin state. So just like for atoms, selection rules for molecules dictate that these absorption processes only happen between states that have the same multiplicity. So we can do a transition from a singlet to a singlet state or a triplet to a triplet state, but a singlet to triplet absorption transition is forbidden and is not observed experimentally. And so shown at the bottom of this slide, I've shown you how a singlet to singlet transition might occur. So I'm using the middle part of my diagram as my initial state. So going from the middle to the left is totally an allowed transition, but going from the middle to the right is a forbidden transition. And what may surprise you about that a little bit is typically triplet excited states are a little bit lower in energy, more likely to obey Hund's rule. But it's the singlet to singlet transition that actually can be excited by light. A second principle that we need to be aware of is that electronic transitions happen fast. 10 to the negative 15 seconds is, from a molecule's perspective, near instantaneous. And that is way faster than the speed of nuclear motion. The implication of this is that we depict absorption as a vertical transition, meaning that the molecule gains energy. We change our position on the y-axis, but it does not change geometry or its bond lengths, so we don't change things on the x-axis. This idea is called the Frank-Condon principle. And you'll notice on my diagram above, I chose to depict that absorption transition using a vertical arrow because a diagonal arrow would indicate that somehow my molecule is simultaneously changing both its energy or its electronic state and its bond lengths or its geometries. And that doesn't happen. Absorption is a vertical process. There's a second follow-up or half to the Frank-Condon principle, and it's a proof that the transition dipole moment for electronic transitions, again, that transition dipole moment is what governs the probability of a transition, is proportional to the overlap interval between the initial and final vibrational states. And so it's helpful as chemists to compute what's called a Frank-Condon factor, magnitude of the overlap squared, because where that factor is large indicates to us what transitions are most likely to occur. So you'll notice that on this diagram, I'm showing now not only the two different electronic states, their vibrational fine structure, but I'm also showing the wave functions associated with each of the vibrational states. And what the Frank-Condon principle means in practice is that if we're starting off in our vibrational ground state, and at room temperature, we are going to start off in the vibrational ground state, where our wave function and our probability of the molecule being is large is at this coordinate right around here. So our starting nuclear coordinate is most likely to be where the wave function has its largest value. When we're thinking about the final state, you might think that the molecule would go up to its vibrational ground state in the electronic excited state. However, here, the amplitude of the wave function is not too large. So while this transition can and sometimes does happen, it's not very probable. The most probable transition for this particular setup is into the nu prime equals 2 state, because this is where we have a large amplitude of our vibrational wave function. As a kind of neat practical tip, notice that for our vibrational wave functions, most of the wave function amplitude occurs near where our potential energy function happens. And so typically you draw these vibrational or these electronic transitions up to the vibrational state that is close to where that potential energy surface and the energy level cross. Those are called turning points. And so the hope is that if I give you a diagram that looks like this, you'll be able to see why it is that a transition from the nu equals 0 state in the ground electronic state up to the nu equals 2 state is most probable. And hopefully you also see that if we shift the positions of our electronic ground and excited state, that's going to change what vibrational state is most probable for us to transition into. After we absorb a photon, there are many different ways that this molecule can get back to its original ground state. One process that's involved in getting back to the ground state is vibrational relaxation. So once we're in the electronic excited state, the molecule can undergo what's called non-radioactive decay. That means that the molecule is losing heat, is losing energy in the form of heat rather than in the form of light. How this happens in practice is that the molecule can collide with other nearby molecules, give away some of its vibrational energy to the other molecules, which can then be either rotationally or vibrationally excited. Molecular collisions will eventually help the molecule reach its ground vibrational state within the electronic excited state. This non-radiative decay process, when it helps the molecule decrease its vibrational energy, is called vibrational relaxation. And by convention, instead of using a straight arrow to depict that transition, we use a little squiggly arrow to do so. Vibrational relaxation still happens pretty fast as far as the molecule is concerned, something on the order of 10 to the negative 12 to 10 to the negative 10 seconds, but nowhere near as fast as the absorption process. Once we're back into the vibrational ground state, getting back to the electronic ground state is going to take some time. And there's multiple ways that the atom can do this. One possible process that you've probably heard this term before, at least with respect to light bulbs, is called fluorescence. Fluorescence is a type of radiative process where we emit a photon of light so that the molecule can travel back to the ground state. A couple things to note about fluorescence is, first of all, we call it spontaneous emission because we don't need external energy in order for the molecule to want to go back to the ground state. Secondly, fluorescence is specifically used as a term to describe allowed transitions. So if E1 and E0 correspond to, or if E0 corresponds to a singlet state, then what would make this a fluorescence process is if our excited state is also a singlet. So moving between states that have the same spin character is an allowed transition, and that's what leads to fluorescence. The timescale is a little bit slower than vibrational relaxation, something on the order of 10 to the negative 9th to 10 to the negative 6th. So fluorescence takes a while before it actually happens. And that means that typically the molecule has time to vibrationally relax before it fluoresces. Just like absorption, fluorescence obeys the Frank-Condon principle. We depict things as vertical transitions. We need good overlap between our vibrational wave functions in both the excited and the ground state. But otherwise, it's a fairly straightforward process. There are many applications of fluorescence in fields ranging from engineering, light bulbs, to biology, where we can use fluorescence to tag certain proteins and understand how they're moving about in the body. In fact, we can even use fluorescent properties of nanoparticles for drug delivery and trying to assess where we might have cancerous particles present in our bodies. The other thing to note in passing about fluorescence is that because vibrational relaxation is allowed to occur, the energies associated with fluorescence are a little bit smaller than the equivalent absorption frequency. However, fluorescence is not the only way that a molecule can lose energy and get back to the ground state. A second type of process that can occur that's far more lengthy is what's called an intersystem crossing followed by phosphorescence. So occasionally, a molecule might have multiple excited states that it can be part of. And what I'm showing on this diagram is both the triplet and the singlet excited states, where I'm using a dark green color to depict the triplet state and a lighter green color to depict the singlet state. Based on our kind of abstract energy level diagram that I showed above, this corresponds to our singlet versus our triplet excited state. And while we can't directly absorb a photon to get to the triplet excited state, we can undergo an intersystem crossing as a non-radiative process, or again, through molecular collisions and something called spin orbit coupling. We can transition from the singlet excited state, lose a little bit of energy to get to the triplet excited state. Once we're in the triplet excited state, we're kind of stuck because going back to the singlet ground state is now a forbidden transition. That doesn't mean that this process never happens, it just has a very, very low probability. And consequently, the radiative process called phosphorescence, whereby we undergo a triplet to singlet conversion, takes a long time. You'll notice that compared to absorption, 10 to the negative 15 seconds, or even fluorescence, 10 to the negative 8 seconds, let's say, phosphorescence takes almost the age of the universe to go through, 10 to the negative 3 to maybe even hundreds of seconds. So that is a difference of at least 10 orders of magnitude. phosphorescence is slow because we're going to stay in that triplet excited state for a very long time before we can undergo that forbidden transition. That has a lot of implications for biology and for fun because it allows certain biological organisms to emit light far after the sun has gone down and it's been able to absorb those photons such that it glows in the dark. Or our glow sticks, when you break your glow stick to start and shake it to start having it emit light, that's a phosphorescence process where you're undergoing a chemical reaction to go up to the excited state, and then slowly, occasionally photons get emitted in a phosphorescence process. So when you think phosphorescence, think glow sticks, and you know how long those last, many hours, and it's because of that forbidden transition between the triplet and the singlet state. Pretty cool. Now, you may have noticed, I'm starting to, I deleted fluorescence from my diagram, and it still looks like I have a lot of arrows and lines on top of each other. So the last thing that I want to talk about for today's lecture is one way that an alternate depiction for showing what all these different possible transitions look like. And these are called Jablonski diagrams. So previously and up until this point, I've had the x-axis be a meaningful amount of information. It's depicting a nuclear coordinate, like a bond length. If we want to try and space out the lines on our diagram, Jablonski's choice was to remove all of the x-axis information, such that on a Jablonski diagram, the x-axis is meaningless. It's just spaced out for aesthetic purposes. And similarly, for all of the different states that are shown on the Jablonski diagram, the length on the horizontal axis of these states doesn't mean anything. It's just there for aesthetic purposes, so we can show all the transitions without overlapping lines. The y-axis, however, is still meaningful. It represents energy. In using a Jablonski diagram, hopefully you can see that all the types of transitions that we just discussed can be present simultaneously on one diagram. Not to show the process of what is happening to the molecule, but to show what could happen to the molecule. And so you see on a Jablonski diagram that we'll use notation S and T to represent singlet and triplet states. And we'll use subscripts to represent if we're in the ground state, 0, so S0 is our ground state, or if we're in excited state. If we have multiple excited states, for in this case, this Jablonski diagram shows that there's 2 different possible excited states that are still have the molecule in a singlet state, then we'll use increasing numbers to depict those. And so obviously with a Jablonski diagram, some information is lost. It's really impossible to infer from a Jablonski diagram the geometric info about a molecule, how the geometry might change as we're in the ground state versus the excited state. And similarly, you can't really see from this diagram or infer what the Frank-Condon factors should be. So it's kind of hard to know which of the various absorptions that are shown on this diagram would be the most likely to occur. However, the big advantage of a Jablonski diagram is its visual clarity and our ability to space out the arrows so that they don't overlap. All right, and that's all that we have to talk about today. So this has been a lot of information, but let's try and focus on some big picture takeaways about electronic spectroscopy. Our first takeaway is that electronic wave functions for atoms are described using term symbols so that we can talk about the atom's wave function, electronic wave function, rather than focusing on each individual electron's wave function. They're formatted using the multiplicity as a superscript in the upper left-hand corner and some letter that describes the total orbital angular momentum of an atom. For polyatomic molecules, Jablonski's notation is a little bit simpler. We simply use a letter to describe if we're in a singlet or a triplet state, and we use a number in the bottom to describe if we're in the ground state or a certain excited state. Especially for molecules, many processes, some that are radiative, some that are non-radiative, can lead to vibrational and or electronic transitions. And a lot of times electronic transitions induce vibrational transitions. A list of their possible transitions and the typical timescales associated with these transitions are depicted on the diagram that I've shown below. And I think what's really important to note, and I should add this as a takeaway, is that for these transitions that are electronic transitions, while sometimes there's additional selection rules for atoms, the selection rule that's true for atoms and molecules is that our spin state should not change. And we saw that that was really important for why it is that fluorescence is a fast process and really only occurs for the duration of when you have your lights on. As soon as you get rid of your absorption process, fluorescence goes away, versus phosphorescence, which because it's trapped in the triplet state, can linger for seconds or sometimes even hours. And then our third and final takeaway for today is that for radiative transitions, processes that involve the absorption or the emission of a photon, the Frank-Condon principle gives us guidance on how that absorption or emission will occur. We learn from the Frank-Condon principle, first of all, that transitions are vertical, i.e. they do not involve changes in the nuclear coordinates. And second, we learn that the most probable transition is to a vibrational state that has good wave function overlap with the initial state at the nuclear coordinate where the transition is set to take place. And so with that, that's all that I've got for us today on electronic spectroscopy. I look forward to seeing you all come lecture and come in class. Take care, folks.